Hello, everyone. Thank you for coming to our presentation. I'm currently a postdoc in University of Florida, and this is my work completed during my PhD program in the Vanderbilt University. This is a joint work with Clemson University and University of Central Florida. Our work is graphics peeping unit exploiting EM side channel information on GPUs to eavesdrop on your neighbors. As we know, discrete GPUs has become increasingly popular in modern computers. They are not only used for high-quality graphics rendering, but also used for intensive parallel computing. As many GPU tasks operate on sensitive information, there has been concerns about potential information leakages. And several recently developed attacks have justified such concerns. However, all these existing attacks, they either need the attacker to physically access to have logical access to the GPU, or the GPU is physically accessible to the attacker. So our question is, what if an attacker has no physical or logical access to a GPU? Is it still possible to implement such attacks to steal the sensitive information from it? And in our work gives a yes to this question. And to the best of our knowledge, this is the first work achieving this. Before going into the details, let's take a look at a feature called DVFS, standing for Dynamic Voltage and Frequency Scaling. Basically, as the GPU power consumption has become a radical problem, DVFS was used to mitigate it. Basically, it specifies multiple performance levels. Each level specifies a setting of voltages and frequencies for the GPU cores and memory. And the GPU DVFS will tend to adjust the performance levels to meet the current computational need. So different computational activities will create different GPU workload patterns intermittently. So there will be multiple GPU performance level switching behaviors during the activity. And as we know, different activities generally create different workload patterns. So an attacker may use such performance level switching behavior to infer the computational activities. And more interestingly, we find that we don't even need to know a full picture of the performance level switching behavior to infer the activity. An attacker only needs to focus on a certain level to see whether it's switched on and off to know the information. So now that we know an attacker can use this level switching behavior to infer the user activities, back to our original question, without any access, how can an attacker achieve this? Well, we found that when a performance level is switched on and off, there are certain EM signals that will appear and disappear at the corresponding memory clock of the GPU. And some further study indicates that this EM emission is generated by the GDDR write clock. Here, let's see an example. We see AMD's popular GPU, RX 580, which has 3 performance levels. If we focus on the second level, which has the memory clock frequency 2000 megahertz, when this level is on, we can see some clear patterns in the spectrum. And when this level is switched off, there's no such signals. So now that we know an attacker can use the EM signals to know whether a performance level is switched on or off, which level should he focus on? Some statistical analysis indicates that the second lowest level is the best choice. If we focus on the second lowest level and collect the spectrogram while opening 3 different applications, we can clearly see some horizontal stripe patterns in there, which can be used to infer which application is being opened. And to simply verify that such patterns are correlated to the performance level switching, we simply capture the trace of the GPU memory clock frequency and using the AMD GPU driver. And we plot the average magnitude along the time axis in the spectrogram. And as we can see, these 2 traces match very well. However, the exploitability of such signals is limited if we rely only on those stripe patterns. There are basically 2 problems. First of all, like all the other clock signals in a computer, the GPU memory clock implements spread spectrum clocking to reduce the intensity of the EM emanations, which means it can be easily attenuated to a level as weak as the background noise. For example, here we can see a signal collected from 6 meters away, where the signal becomes too weak to show any stripe patterns. So we solve this problem by applying the technique called folding. Basically, when a signal is modulated by the SSE, there will be a series of subclocks with the fixed interval f sub m equal to the modulating frequency of the SSE. And accordingly, in the DFT results, there are some periodical bins with a fixed interval delta. To apply folding, we simply sum up these periodical DFT bins at different locations. And as we can see, only when the correct subclocks are selected, we can obtain a maximum value. And what's more important, even if the signal's intensity is as low as the background noise, the folding can still effectively identify those subclocks and enhance such signals. So what if we apply this folding to the original spectrogram and collect the energy at all subclocks and recover a time series trace? As we can see some clearly patterns corresponding to the periodical workload. But even with this folding technique, other problems can occur with the presence of some strong background noise. For example, here we can see some strong background noise near the frequency of 800 megahertz. If we apply folding directly in the recovered time series data, it's dominant by this strong periodical noise. So to remove such noise, we simply apply a filter. And the effect is that if we try to sum up the DFT pins at any random locations, the expectation of the sum up value will be 0. And only if the subclocks are correctly selected, the expectation will be a positive value. As we can see, when we apply such technique, such a simple filter, we can successfully remove all those noises and preserve only the pattern corresponding to the periodical workload. So with such signal processing techniques, an attacker can easily exploit such signals with only a simple SDR device and an RF antenna. To better understand the impact of this newly identified leakage, we evaluated 6 different GPUs covering the low-end and high-end products of AMD and NVIDIA released over the past 6 years. Now you may wonder, how far can such attacks be launched? So according to this figure, the distance depends on the directions. And except for the NVIDIA's RTX 3060 GPU, most GPUs, they can transmit signals to several meters away in all directions. And even for RTX 3060, the distance can be longer than 2 meters in most directions. As we can see, although using an all-metal case can make the things a little better, there are still some directions where strong EM leakages can be detected. We also test if such signals can be collected from the outside of an apartment. As we can see, the plaster wall used in an apartment has negligible impact on the signal intensities, although the concrete wall can attenuate the signal more, but this amount of attenuation is still manageable with our signal processing technique. So we performed 2 case studies exploiting this leakage. The first is so-called website fingerprinting attacks, which is to infer which web page is visited by a user. Basically, modern web page browsers will use GPU to help website rendering, like rasterization and image composition. So rendering different web pages will create different workload patterns, which of course will create different performance level switching behaviors, as demonstrated by these examples. So an attacker can use this information to know which web page is being visited. To evaluate this attack, we selected 50 websites to be opened in the Google Chrome browser. And for each website, we collect the signals at different spots defined by the distance and the directions. At each spot, we collected 50 EM traces to train a DNA model and classify the time series data. we use the data collected from 2 directions for training and the data collected at the other directions for testing. Now let's see the results. As we can see from the confusion metrics and the prediction results, prediction accuracy, this attack is successful in all tested GPUs. Even though some GPU like RTX 3060, the accuracy is relatively low, this 63% accuracy still gives the attacker enough information most of the time. And actually, a real attacker can use data collected at any spot for training. So if we use more data collected from more spots for training, we can obtain an even higher accuracy. And similarly, if we perform such attacks from a faraway scenario, we can also successfully implement such attacks for the tested GPUs. The second case study is to infer the typed keystrokes and learn the inter-keystroke information. Basically, this information can give the attacker knowledge like the password length, and although the typed word cannot be directly revealed, this inter-keystroke timing information may be exploited to recover the typed key pairs, because typing different key pairs will actually take a different amount of time. So when we type in a web page, it will create some GPU workload like re-rasterization or recomposition. Here we can see when we type A, B, C with the time interval 200 milliseconds and between A and B, 350 milliseconds between B and C, and 500 milliseconds between C and A, we can clearly identify each keystroke and learn the inter-keystroke timing information. We also evaluated a more practical scenario where we ask real people to type username and password on the Facebook login page. We can see every keystroke, including the tab, can be successfully identified. So we evaluated such keystroke timing attacks on different GPUs. It turns out that AMD GPUs are less vulnerable in this case. RX 580 is the only GPU that can leak keystroke information for AMD products. And the time resolution is worse compared to the NVIDIA GPUs. On the contrary, all NVIDIA GPUs can leak very detailed information about the keystrokes, which means this can be implemented to recover keystrokes with very short intervals in between. Now you may think we can easily fix this by disabling the GPU DVFS, but unfortunately that's not the case. First of all, it will hurt the performance or energy efficiency. But more problematically, it may not even be effective for the case of NVIDIA GPUs. After we do this, we find some new exploitable EM signals at the 1/8 data rate that can be AM modulated by the activities. And what's even worse, when we try to use such signals to perform the website fingerprinting attacks, we can obtain an even higher accuracy. So how can we countermeasure it? Here we provide several possible solutions. EM shielding is a straightforward way to attenuate the signals, but as our previous evaluations indicate that even in an all-metal case, the GPU will generate strong EM leakages. So we believe more careful engineering efforts are needed to implement this. And jamming the signal frequency band using strong noises is another solution. But as our signal processing techniques are kind of resilient to random noises, so we believe maybe the noise needs to have very high intensity. And reducing the sensitivity of GPU DVFS will definitely reduce the signal's time resolution, but it may hurt energy efficiency. We can also obfuscate the original GPU usage pattern by running some random workload. It's an easy to implement method, but it may inevitably induce some overhead. So in this work, we found that the GPU DVFS will inevitably induce some leakages by performing the workload-dependent performance level switching behaviors. And we can use the EM emanations to identify to detect such switching behaviors. And we also proved that this new leakage can be exploited to launch practical attacks like website fingerprinting attacks and keystroke timing attacks. And we also find eliminating such leakages is kind of challenging, so we believe that more efforts are needed in the future to handle this. Thank you for listening. Do you have any questions?
If there are questions here, please come to the microphone, introduce yourself and your affiliation. And anyone online, please write your questions. Until then, you mentioned in your talk that you used the second performance level.
Yeah.
And in GPUs that have 3 performance levels, I can understand why this is useful, because that's the middle between, you have to cross it when you go between the extremes. But why would what did you use on other GPUs when you have more performance levels?
Oh, actually, all our evaluated GPUs, they not necessarily have 3 performance levels. There are some GPUs, like many NVIDIA GPUs, they have 4 or 5 performance levels. Like that's only an example for RX 580 that only has 3 performance levels. So actually, like all these evaluated GPUs, it has multiple performance levels. And, yeah. And we found for all GPUs in the second lowest level is like mostly frequently switched to, so that level will leak most information compared to the others.
Okay, thanks. And all the GPUs you have tried are GPU on cards that in extension cards. What about the GPUs that are embedded in the processors? Have you tried those?
For those embedded, integrated GPUs, that's another problem. Like this DVFS technique, it's independently implemented for the discrete GPUs, and those integrated GPUs, those are performed. The voltage are regulated by the CPU VRMs, so that's like not in the scope of this work, but definitely we can do some further investigations for those GPUs.
Okay.
Hey, so for defenses, you proposed the Faraday cage, and then you said maybe it wasn't that effective because you tested with metal-cased GPUs. Am I understanding that correctly?
Yeah.
Was that the metal case of the GPU, or the case of the PC the GPU is in? Oh,
actually, that's a case of the PC.
Okay.
Basically, we like evaluated measure the distance at 2.
Got it.
Oh, sorry. Measure the distance at 2 different type of cases.
Got it.
Yeah, one type of case is like completely metal. So even in that cases, we can measure some strong EM leakages at some distance away.
So do you think a case that was designed specifically to block EM signals would work better, or no?
Yeah, we believe if there is some case especially engineered to protect from EM leakages, that may be a better solution.
Would it be a complete solution, or do you think it will still leak?
It depends on how fine that EM shielding effect they can achieve. But I believe there's definitely some engineering work needed there.
Got it. Thank you.
Thank you.
Okay. Before we thank Zhan again, I would like to mention that Zhan is on the market, is looking for a place to continue his great work. So if you're interested, please contact Zhan. And let's thank him again.